Now we want to actually work to apply these counting units to chemistry. So we've actually already seen it before and didn't really call it a counting unit in the form of a molecular formula. If we think about a molecular formula, for example, if I have ethanol, C2H6O, here's my structural formula over here. And I can see that what this molecular formula tells us is that in one ethanol molecule, I have 2 carbon atoms. That comes from that subscript on the carbon. I have 6 hydrogen atoms right there. And I can see that I have the 1 oxygen atom, which is that lack of subscript out there. And so these are counting relationships, the number of atoms in one molecule. A molecule is a group of atoms, right? You're grouping all these atoms together and defining a new object to count that we call molecules. And so we can actually use this as a conversion factor to change what we're counting. One C2H6O molecule is the same thing as having 6 hydrogen atoms. So that relationship could be true for any sort of atoms inside a molecule. That molecule is a package that holds, some sort of number of atoms together in that. So let's see how we can use this. How many carbon atoms are there in 1.45 times 10 to the 5th molecules of ethylene glycol, which is C2H6O2? So if we want to talk through the problem, we always want to start with what do we want? What do we want in the end? Specifically, what sort of units are we after? And we can see in this case, that is number of carbon atoms. We're looking for a number of carbon atoms. And we've got to think about then what do we have? What sort of information is present? Basically, what already is a number that we're given? And we can see it's this 1.45 times 10 to the 5th C2H6O2 molecules, right? This is the number of ethylene glycol molecules that are present. So we want number of carbon atoms. We currently have number of molecules. Molecules right here are objects, right? They are countable objects. So when we have that sort of number, that's just when we're given that value, it's a number of molecules. We want number of atoms inside those molecules. And then we can relate these via the molecular formula. If we want to know the carbon atoms, there's some carbon atoms in each molecule, so the molecular formula tells us that relationship. Now let's take a look at actually working that out. How many carbon atoms are there in 1.45 times 10 to the 5th molecules of ethylene glycol? Molecular formula, C2H6O2. So again, we've seen that what we want is carbon atoms. How many? That word means we're looking for a number of atoms, we're counting them, and we started with 1.45 molecules. So if we want to think about this problem when we set it up, we started with the 1.45 times 10 to the 5th molecules. We want to go into carbon atoms. So the conversion, the question there is, well, every molecule of C6H12O2, how many carbon atoms? Again, this kind of setup is always going to work out. Those molecules cancel out, the atoms. Oh, sorry, you'd be left with atoms. You're not canceling out atoms. So you'd be left with atoms. Sorry about that. And so the question is, what do we have here? Relationship between these. And this is the same idea as the dozen, where the group is in the molecule. So we define one molecule of C2H6O2 is going to be equal to 2 carbon atoms. And when we're looking at this 2, we find it right there, right? Because the package, the group that we call a molecule, is contained of a certain number of each type atom. And we can see that the 2 comes from that subscript in our molecular formula. If we were asking about hydrogen, it would be 6. If we were asking about oxygen, it would be 2. So we can always do that relationship. So when we multiply this, when we put them in, we put a 2 right there and a 1 right there. So 1.45 times 10 to the 5th times 2 divided by 1 gives me 2.90 times 10 to the 5th carbon atom.